Hello there, it's biomod2 team. Here's a video to present you version 4.2.6 of our package. Species distribution modeling, says Wikipedia, uses computer algorithms to predict the distribution of species across geographic space and time using environmental data. It is widely used nowadays, but there is a lot of algorithms developed, and it is often quite hard to decide which one is the best to be used. Indeed, numerous models are available, ranging from classic regression and point process models to discriminant analysis, clustering, decision trees, envelope models, and neural networks. Since the emergence of computer science and species distribution modeling, a lot of analyses have been done, comparing different modeling techniques or algorithms, and even in the recent years, it can remain unclear which model should be used in which circumstances. Which leads to the need for a platform to apply easily different models on one's data, to be able to compare the results of these models, and in some cases, to even go a step further and combine them into ensemble models, allowing the user to both explore variability in results and make the most of the advantages of each model. biomod2 is an R package developed by the LECA since 2009 that fulfills these three requirements. R language is nowadays commonly used in scientific teams, and we use platforms such as GitHub for development and Cran to help and publish the different versions of the package. Moreover, we did a lot of work these last years improving the documentation, examples, and tutorials available for the community through a website. Since 2021, we worked on several short, mid, and long-term development plans. Cleaning of code, reorganization of files, and solving bugs were carried out together with improvements of documentation. We added new possibilities for pseudo-absence selection or cross-validation, and new models such as XGBoost or random forest downsampled. This year, we worked a lot on a new way of setting models options, which was a required step before going towards abundance models. A lot of graphical representations guiding you through how our package works are available on our website, but we try here to present it in a way that fills the gaps. First thing first, biomod2 presents an ensemble of functions available to the user that are divided in 4 categories. 6 main functions can be called to carry out the main modeling steps. They will return biomod2 objects that can be used to perform the successive steps. These main functions sometimes rely on what we call secondary functions, which are functions that can also be used independently by the user if he wants to go in more details on specific steps, for example, such as options tuning. Then come the getters functions that can be used to extract specific information from the output objects obtained from the main functions. Finally, some plot functions are available to extract and render some information from the main outputs. Note that, as it is impossible to have the perfect plot for every situation and requirement, these plot functions always return both the ggplot object produced, which can be modified afterwards, and the data used to create this ggplot object. And now, we'll go together through these different modeling steps. We will use the biomod2 example data, which contains both coordinates and occurrences for 6 species at the world scale, and environmental variables extracted from BioClaim. We will carry out the example with the gulo-gulo species, but do not hesitate to try with another one. The first step is to gather and format our data into a standardized object that will be understood by all biomod2 functions. This is done through the biomod formatting data function, and here is a detail of the different type of relevé dataset you can provide. The data that will be used to build your models will be called your original dataset from here. Original data can contain 2 types of relevé, either presence-absence points or presence-only points, which are the most frequent and meaning that no information is available about places where the species of interest is not. In the presence-only case, Pseudo-absence points will be drawn to represent the available environmental conditions within the studied area. Whether it contains only presences or both presences and absences, this data will be divided into calibration validation datasets. One part of the data will be used only to calibrate the models, and the rest will be used to compute some metrics to estimate how good the models are on new data. Note that if you have presence-only data and created pseudo-absences datasets, each of these datasets will be divided into calibration and validation parts. Splitting up data into calibration validation datasets is the most common way of estimating how good your models are, but not the optimal one. The perfect modeling situation would imply that you have at your disposal what we will call an evaluation dataset, composed of presences and absences that have been sampled in a completely independent way of your original data. However, this is not often possible, and most simulations are done using only original data. Finally, all your calibration validation datasets will be associated with a set of modeling options for each model to be used. Note that modeling options can be parameterized in the same way across all runs or across pseudo-absence datasets or for each run separately. If you remember what I told you about main and secondary functions, here is a good example. Biomod formatting data will take care of data gathering and creation of pseudo-absence datasets, but you can also create on the side your pseudo-absence datasets with the BM pseudo-absence function. Similarly, calibration validation datasets and modeling options can be directly defined through the biomod modeling function, but BM cross-validation and BM modeling options secondary functions can be used separately to execute the steps. Now, let's go back to our gulo example and start with the simplest case with presence-absence data. Here, we provide the biomod formatting data function with a species name, a vector containing 0 or 1 values, the corresponding x and y coordinates of those points, and a raster object containing environmental variables matching the releve extent. If you print your output data, you will have a resume of the information you provided. That is your species name, the number of presences, true absences, and undefined points, as well as a summary of your explanatory variables. You can also plot your formatted data to visualize your dataset. Here, blue points represent presences of gulo and red points the true absences. As we are here in the case of a complete dataset, we assume that we know the entire distribution of the species, and points that are no presences are considered as true absences. But keep in mind that it is an example set. And now we'll see briefly how to add evaluation data to our dataset. The principle is the same as for original data. You have to provide occurrences, coordinates, and explanatory variables for your evaluation dataset. If you print your formatted object, you will see the details for your two datasets. On the top, the original one that will be used to build the models, and below, the evaluation one that will be kept to evaluate the computed models only. The plot will show you as well the two datasets. As you can see here, I just subsampled the original data to show you how to add evaluation data. From now on, we will not use anymore the evaluation dataset in the examples for clarity's sake. The next step presents you the most common data case, which is presence-only data. Hence, we will have to select pseudo-absences to complete our data, and there are several ways to do so. We have 3 methods implemented in biomod2, and I will present you right away a simple questioning scheme to help you decide which will be the best suited for your data. The first 2 methods can be chosen if your data has been obtained from a sampling design which has been, in a reasonable extent, exhaustive. Then it depends on whether the sampling has been done geographically or environmentally. On the left, you can see a map of Madagascar island, and colors represent IUCN ranges of 9 lemur species. We know exactly, at a certain resolution, where the species are geographically located on the island, but the sampling was not done regarding any environmental rules or filtering. In that case, I can use the disk method to sample my pseudo-absences to model these species, as I know that as long as I go away from the ranges, I will not find them. Note that this can be due to other factors, such as biotic interactions with predators or humans, but this is another point and we'll keep it simple here. Now, another example still on Madagascar island. Let's say that I'm sampling a plant species known to grow only on 2 types of bedrock, and we have the map of the island bedrocks. Knowing that, relevés were only done in the areas matching the plant's bedrock preferences. We can say that the sampling was environmentally oriented and complete, and use the surface range envelope method to sample our pseudo-absences, provided that bedrock is included in my explanatory variables, of course. Finally, imagine that part of my data was following a sampling design but not the rest of it, or that some bias might have been introduced in the sampling, whether it was through the sampling method, the observers, how the study area was first delimited, or how the modeling question was first asked. Then I should go for the random selection of pseudo-absences to be sure not to add any more bias in my analysis. Note that if you hesitate at any point of the questioning, the random method remains the safer. After that comes the big question: how many pseudo-absences should I sample? Unfortunately, there is no magical formula that can give you the answer. It depends on your data, on your resolution, on your sampling. What you must keep in mind is that you don't want to take too little, or you risk missing out on certain environmental conditions, or take too many and face overestimation. And the best way to check that is going through the variability of your results to see whether you have big differences in evaluation metrics between your different pseudo-absence datasets or not. Also, there has been a few attempts to estimate this number depending on the modeling techniques, and some rules can be extracted from that. It remains dependent a lot on your data. To deal with that, we added a new feature in our pseudo-absence sampling method to allow you to select pseudo-absence datasets of different sizes and to attribute them to different algorithms if wanted. Just keep in mind that it is not possible in one analysis to mix the different pseudo-absence selection methods. You have to choose between the disk, surface range envelope, or random method. Let's try that with our glow species, starting by transforming absences into NA, meaning points in the study area that are no presences but can be selected to be pseudo-absences. Here, you need to give some additional parameters to the biomod formatting data function to specify the number of pseudo-absence sets you want to build, how many points you want to select within each set, and the strategies chosen to select them. I present you first the most commonly used random method, and you can see on the right the print of the output containing at the bottom one line regarding the pseudo-absence datasets. Summary and plot functions can be used as well to get an overview of my formatted data and each dataset prepared. Differences with the disk and surface range envelope methods will be seen here mainly in the parameters to be given and visually on the graphics. What you must keep in mind for the disk method is that minimum and maximum distances from presence points to sample pseudo-absences must be given in the same unit than the projection used for your coordinates and variables maps. Here, the projection used is WGS84, which is using degree units. So as you can see on the graphics, it means that pseudo-absences must be at least 10 degrees away from presence points and maximum 100 degrees away, which is off map here. As for the surface range envelope method, the quantile parameter can be interpreted as follows. 0.01 here means that the 1% most extreme values of each variable on each side of its distribution along its gradient so 2% in total, will not be taken into account to determine the tolerance boundaries of the species. Hence, the lower this number, the less pseudo-absences will have environmental values that can be encountered in a presence location. You can note here that the pseudo-absences per soil distribution is not so different from the one obtained with the DISC method, except in Greenland that is too close in environmental conditions from the species area, even though it was far enough from the DISC method point of view. I mentioned previously that it was now possible to create multiple pseudo-absence datasets of different sizes. For example, to test the effect of the sampling effort over the performance of one model, or to give different settings to different models. It is quite simple. You just have to specify to the PA number absences parameter, instead of one number, a vector containing as many values as the number of repetitions asked for. Here, I want to build 4 pseudo-absence datasets, one with 1000 points, 2 with 500 points, and one with 200 points. You can see in the function print the different steps for each requested size. Once again, if you print your formatted data, on the right of the screen, you will see a bottom line specifying the size of your different pseudo-absence datasets. The summary function will also be of help, and the plot function allows you to see in one glance the difference between your datasets. This was the last possible step of the biomod formatting data. Now, our dataset is ready and we need to go to modeling choices. The first one will divide our data into calibration and validation parts and can be done through the BM cross-validation secondary function to fully explore all the possibilities. We will start with the simplest case, presence-absence dataset. The function is simple. You have to provide your formatted data from the previous step, select your strategy to split your data, and some additional parameters depending on the chosen strategy. And as for the pseudo-absences selection, the simplest one is a random strategy. Here you ask to keep 70% of your data for calibration and the remaining part for validation, and to repeat this process 5 times. The output of this function is a data frame with as many lines as observations, either presences or absences, and one column for each set, specifying whether or not the observation is taken into account for the calibration, the rest being kept for validation. You can also use again the summary function applied to your formatted data object, but providing in addition your cross-validation selection. In the same way than before, you can plot your formatted data together with your cross-validation selection. Note here that I switched the plot type parameter from points to raster, as I have many points to render. Now, there are other methods implemented to split your data. I show you just another one, the k-fold strategy. Here, it will randomly divide your observation in 3 and create 3 cross-validation sets, each one using as validation data one of the 3 parts. And the process is repeated twice, so you end up with 6 cross-validation datasets. The process is completely similar if you have presence-only data and sampled pseudo-absences. The main difference is that the number of cross-validation sets will be multiplied by the number of pseudo-absences repetitions, and so will the number of runs to model. So here is the same example for the random strategy, but starting from the formatted data for which we created before 4 pseudo-absence datasets. As you can see, the number of cross-validation sets is going up quickly. You can also notice that some columns contain NA values. You have to keep in mind that each pseudo-absence dataset is already a subsample of your study data, keeping all presences but only part of the remaining points, and each cross-validation repetition is done on each pseudo-absence dataset. The summary gives you an overview of each combination of pseudo-absences and cross-validation. And the plot shows you the distribution of these different combinations. Let's now start talking about the modeling in itself. biomod2 can actually be seen as a fun switchboard. It has a defined list of packages in its number directory that it can call. These packages contain modeling functions that will then be used by biomod2. And we have two exceptions to this automated workflow: the surface range envelope model, which is directly coded in biomod2, and Maxent, which requires a specific coding as it is calling an external software. Another advantage in this automated call workflow is that we now can extract directly all available parameters from the called function itself. Let's take the example of GLM. The GLM function we use is included in the stats package and contains a list of parameters it can understand that are listed here in the args names item in this model ID card. Some of those parameters already have default values, and we retrieve them as well. All of those informations constitute the GLM ID card and are independent of any user value. As soon as we start adding data, we encapsulate this object into another one, which duplicates arg's default item into a new one, arg's values, which is a list that will contain as many replicates of parameters values as run in the modeling process. These values can be parameterized in different ways, either with default values, which are the ones extracted directly from the function, plus a few minor corrections to be sure the model will run, either with big boss values, which contain more changes made by the biomod2 team to try and optimize a bit more the model. Keep in mind though that these parameterization choices remain broad and might not be the more adequate depending on your data. That's why you can also choose to tune some of the parameters onto your data, whether it is on the whole dataset or on each specific run. And finally, you can decide on your own or use a mix of these methods. Within the ID card are detailed the model name, the data type, the package it is coming from, and the function name. These four informations combined represent the ID name of the model. And this information can be found within the biomod2 models table data. You just need to juxtapose the first four columns to get each model ID name. So this was all the detail for one single model. But how does it work when using several? Let's say here I want to use three models: GLM, Random Forest, and XGBoost. The BM modeling options function will create a biomod object containing first the ID names of the wanted models. And for each of those models, it will store their ID card and the parameterized modeling options within the options list. Pictures are better than 1,000 words, so let's see that in practice. Modeling options can be retrieved through the BM modeling options secondary function. As it will call each selected model and associated package to build its ID card, it does not necessarily need to be associated with data, as we'll show this example. Three models are selected: GLM, Random Forest, and XGBoost. And the chosen strategy is the default one, meaning that all parameters will keep their package default values, except for a few ones that are absolutely needed to ensure models running. The output object is a biomod2 object as presented before. As mentioned previously, if you go a bit more in details, you will find two elements. First, a vector containing the model's ID name, and second, a list containing as many elements as ID names and corresponding to each model ID card with all its parameters and values. There is an automated print for the object, showing you for each model all the parameters and their associated value at once. The Big Boss strategy basically does the same, except that some parameters have been modified by the biomod2 team in order to improve a bit simulations in a general way. You can see on the print the ones that have been changed. Their default values are shown in brackets in blue, nearby the new ones in yellow. Note that these small optimizations might not be the best suited depending on your data or your modeling choices. That's why we'll see from now what happens if we link these modeling options to our formatted data and its corresponding cross-validation datasets. The big bus strategy is kept, but the formatted data is provided, which is the presence-absence dataset here. The first main change is highlighted in pink. A formula has been defined for the GLM model, as it now has access to the species data and the environmental variables. You can also provide the data frame obtained from the BM cross-validation function, which contains 5 calibration validation datasets randomly selected. You can see now the second changes in peach color. The print shows options for a specific calibration set, here run 1. In this case, as the big bus strategy is used, all parameters values are the same between runs, but it is possible to go one step further and try and tune these values for each calibration set. So how does this tuning part work? Remember the fact biomod2 call packages to use their modeling functions? Well, it can also use 2 other packages to tune these models. Most tuning is done through caret package, and enm eval is used for the specific case of maxent tuning. How does it work in practice? Well, it is not so different. You have to select the tune strategy and to provide your formatted data. Note that if you provide only your formatted data object, tuning will be done over all your observations, while if you give also your cross-validation table, each calibration dataset will be tuned, but this will take way more time. What is the difference now between presence-absence data and presence-only with pseudo-absence datasets? Well, not so much, except that depending on what information you give to the BM modeling options function, you might have different number of versions of modeling options. If you provide only your data, you will have as many modeling options as pseudo-absence datasets, as shown in pink on the graphic. If you give a cross-validation table as well, you will have as many sets as combinations of pseudo-absence and cross-validation datasets, the green boxes. Now, there is a final option to define your modeling options, which actually allows you to do pretty much anything you want. Sounds cool, no? But it might seem a bit complex at first. Let's see that together. The idea is to use the user-defined strategy and to give to the function values that you have parameterized by yourself before. This is done through list objects, defining for each dataset the list of parameters names and values to be changed. Note that you do not have to provide all models and parameters if you want to change only a few. All other values will come from the user-based parameter, which can be set either to default or big boss. So here, for example, I only want to modify parameters for random forest and XGBoost, but I keep it simple as I want the same values to be applied over all pseudo-absence or cross-validation datasets, so I use the for all datasets title for that. And then I gather this list of parameters into one with names corresponding to the model's ID names that I remind you can find using the models table data. Previous example was a simple one directly specifying parameter values to be changed, but you can actually give the options part of any object returned by the BM modeling options function. So for example, you can specify some parameters by hand for random forest and run some tuning for XGBoost parameters and combine the two. So you see, pretty much anything you want. And as it is already a lot of information, this video ends here for now, but the rest is coming soon, with details on single models, projection, and ensemble models. See you!